how are we doing, everybody? Good to see you here. Let's hop over to the Kahoot. Got some questions in the chat right now. When will students know when they're taking the makeup exam? Make sure you fill out the Google form for my class, only my class. And if you've done that, I will be putting it in probably later today. So if you've selected one of those times, make sure it's on the Google form. So let me go look at the Google form right here. But how is everyone doing? We are streaming, right? Who's all there? We got Inspired Iguana right there. Let's go look at that Google form. Make sure it's filled out on the Google form. You're welcome, Hannah. Thank you for the question. I have people who just submit the documentation to Canvas, and I'm like, you need to fill out the form. But only for our class, only for our class. The exam too early form. The exam too early form right here. This form for our class. I'm not gonna put the link in the chat because it's not for other classes. It's only for our class. So I have to go in. So I usually just wait to do it till because it's Sunday is the first day to take it early. It's open till, I always hate saying the times without looking at it. Gotta go look at the time. Gotta go look at it. I gotta go find it. If I say the wrong time, you probably are right. But if I say the wrong time, then people will be like, Brian said it was open to this time. And I'll be like, no, oops, whoops. Got that wrong. So I never want to say the wrong time. I'm always afraid to do it off of memory. Like, I think it's Tuesday. I'm always afraid. I was like looking at it and saying it. Due by 11 p.m. Yep. That's what it says is due by. Due by 11 p.m. at night. It's got it right there. Here it is on the screen down there at the bottom. Opens up from 7 to 11. You are correct. It sounded right to me. Opens at 7. Thank you so much, Cameron, right there. Good information. Always afraid somehow I'll get it wrong. Because if I get it wrong once, it's bad. People start being like, well, Brian said it opens at noon. No, I shouldn't even joke. Like, well, Brian said it. And then I'm like, oh no. Let's go here to lobby music, 16-bit. Okay. It's almost time to Kahoot. We only have 28 people here, which means lots of opportunities for prizes. I think you guys can hear the desktop music. You can. It's a little quiet, maybe. There we go. Hey, Emma. Good to see you here. Hey, Emma. I think I met Emma yesterday. I wish it did open at noon, 7. Yeah, I know. It's the reason you might wonder why we only have it open for a certain window is because if we have it open, you're fine, Jax. You can still join in. We'll start here in about 1 minute. The reason we have times for it is that way when we're giving it, if there's any issues, we can be at our computer. If we have it open all day and you're like, I'm gonna take it at noon because I only have this window, then we're having to be at our computers all time. Someone has an issue and they can't take it, then we gotta work around it. So usually from 7 to 11, your instructor should be very available because that's, yeah, so that's the theory behind it. I've had it open all day before when I teach classes like in the summer by myself and then I'm just watching my email. But even then I might go eat some lunch or go to the grocery store and I come back and someone's like, I've been trying to get you for an hour. And I'm like, I just walked out the door. And so, yeah, it's tough because someone's like, I want to take it at 5 a.m. And I'm like, well, I'm not awake then. They're like, that's the only time I can take it. So yeah, that's why we funnel it to one time. Getting some notes up here. My gosh. We'll start with something fun here. You know what it's time for, everyone? We're gonna Kahoot with a special guest to lead us in. Chapter 13 and 14 have a very special mascot. Does anyone know the mascot for chapter 13 and 14?
It's me, the cat named Quad. I'm the special mascot for chapter 13 and 14. Hey everyone, get ready for Kahoot. Brian's getting ready.
Gosh, we brought him to life, the cat named Quant. Okay, let's go. Beautiful, beautiful. You had to be in class to see it. So, if you're wondering how I'm doing it, I've got some other stuff. Here, check this out and then we'll get serious. Where'd it go? All right, maybe I won't be able to do it. Well, it went away and I don't have my other things. Oh, here we go. S2, what's this gonna be? Oh, that's crazy. You can do really cool stuff. I've been working on Been working on a lot of things here. I'll close character creator. Oh, let's get serious. Let's go back to the main screen. He is now part of Stat Tool 1 history right there. Oh my gosh. If you don't have this written down, probably write this down. We've got a lot of notes on the screen, but let's go back to Kahoot. Here's the Kahoot right here. We got 27 players. Let's start in 10 seconds. So if you see the screen right now, join in. And then we'll get serious and we'll start learning. Serious face on. Got some serious faces in the chat. Starting in 5, 4, ready to learn. 3, 2, 1. Put on that serious face and let's Kahoot. Remember, some of these questions might be on the test. First question right here is in 3, 2, 1. Two events that can be easily added together must be what? What must they be? Two events that can be easily added together. And what you want to do right now is you want to go to the formula sheet and look at the formula sheet, and you want to know how to read it. So this is about reading the formula sheet, knowing how to read it. We're going to pin it in the chat right here. So go ahead and answer this if you haven't answered already. But if you have time, go ahead and look at the formula sheet. Remember, take your time. Don't worry about getting these right fast. Worry about getting them right. So if you haven't done it already, go to the formula sheet, which is pinned in the chat right there. I'm going to go over here in a second. But go to the formula sheet. Formula sheet is pinned in the chat. MuBot can bring us the formula sheet at any time. Two events that can be easily added together. And you want to print off the formula sheet before the test. You have the formula sheet next to you. Usually about half the people get this right, half people get it wrong. I've done this many times. And if you look, about half got it right, and about half, literally, wait, how many people got this right? How many people got it wrong?
It doesn't matter.
Wait, is that the wrong one? How many people got it right? How many people got it wrong? Which is bad because that almost means it's a random guess. 18 right, 18 wrong, 50%. Lita got it right. Let's throw 1,000 points for Lita right there. I've been doing this for a while right here. You can have the formula sheet out during the exam. Make sure to print it off and have it out during the exam right there. As I said, I've done this many times, so here's what you want to do, and here's how to know how to do it. So we're grabbing the formula sheet right here. I think I need to unfull screen this, and the formula sheet is going to be under, and it's tagged up there in the chat. So let's go to the formula sheet, and I want to point something out to you. The question was, to add together two events, the things must be what? To add together, like the probability of A or B, that's the word, that's the math, they must be what? So if you go to the formula sheet, and you're like, mutually exclusive. Mutually exclusive. That means if one happens, the other can't. So if you go to the pet store, your parents say you can get one pet. If you get a cat, you can't get a dog. Are your grades in Stat Tool 1 mutually exclusive? Like A, B, C, D, F in Stat Tool 1. Are grades in Stat Tool 1 mutually exclusive? And why? If they are mutually exclusive. Because in Stat Tool 1, if you take it one time, if you get an A, you didn't get a B. If you get an A, you didn't get a C. If you get a C, you didn't get a B. So if one thing happens, the others don't. That means there's no overlap, as though there's no joint between them, like a Venn diagram. And so you have separate occurrences that occur not at the same time. Like think about your favorite football team. Win, lose, tie are all disjoint, i.e. mutually exclusive. Like if I tell you the probability of your team winning this week is oh no gosh. If I tell you the probability of your team winning this week, disjoint is just a synonymous word. Good question, Emma, right there. Disjoint, finish my sentence, is the same thing as what? Like it's just a synonymous word, which means just another way of saying it. Disjoint means the same thing as what? Disjoint, they're the exact same thing. Great job, Sarah, right there. They are the exact same thing. So it's literally synonymous words. So that's why both those answers there are right, because they're the same thing.
It doesn't matter.
Brock knows all the answers. Just either one, because they exclude each other mutually, so they don't occur at the same time. They're disjointed. So think about if one occurs, the other can't occur. This is the way I think about it. Like, let's say it's 100, or let's say today it's 100 degrees out. I'll go with that. Can it snow today? Is snow and 100 degrees out mutually exclusive? Like if it's snowing, could it be 100 degrees? If it's 100 degrees, could it be snowing? So are you saying they can't occur at the same time, right? And if they can't occur at the same time, like probability of snow today is 1%, probability of 100 degrees on any given day in Knoxville is 1%, but the probability of snow and 100 degrees can't occur at the same time. So if it's snowing, the probability of 100 degrees would be 0. So they are mutually exclusive, they are disjoint. Now the other words over here deal with the multiplication rule when we can multiply two events. I'd be scared that like you're burning up and you're like, it's snowing, you're like, what's going on? It's quite a weird day, right? The other rule right here is the multiplication rule, rule number 5. Exactly, Cameron, right? It's so number 5, the rule number 5 is A and B to be multiplied together must be independent. Can anyone give me a definition of independent? Disjoint events are technically very dependent because it's snowing would depend on the temperature, and if it's a very high temperature, it can't snow. But what does independent mean? Like just a definition of the idea of independence. Independence means, well, so independence means if one thing occurs, it tells you nothing about something else occurring. So if two things are independent, like you know this morning that Brian played Pokemon Go. Now, what would that tell you about another random person playing Pokemon Go this morning? We pick another random person out of the world and we say, did you play Pokemon Go? We say, Brian did. Would that tell you anything about them? It tells you nothing. They're completely independent of me. But be careful. If you say, Brian played Pokemon Go, and then what about his wife? Do you think Brian's wife is more or less likely to play Pokemon Go? Is Brian's wife playing of Pokemon Go completely independent of Brian? She's more likely. So do you think she plays Pokemon Go? You think my wife plays Pokemon Go? Because knowing I play Pokemon Go, you might be like, oh, I bet his wife probably plays Pokemon Go. Because she'd be more likely to play. If Brian loves that game, well, he might, yeah. So people are betting yes. You'd bet wrong. She doesn't play Pokemon Go. She loves the games. She loves Red, Blue, Sapphire, what is it, Violet, Diamond, White, is it, I don't know. There's so many. There's the tropical ones. There's the Sun and Moon. There's so many ones. No, she's busy being a vet, exactly. She's saving lives, animal lives. She's too busy for Pokemon Go. But independent means if you know one thing, it tells you nothing about the other. Where dependent means if one thing happens, the other one would be more or less likely. So if you say Brian plays Pokemon Go, it would increase the probability of his wife playing Pokemon Go. Her playing Pokemon Go is somewhat dependent on me playing. It doesn't mean she will play. It just means it changes your opinion. You're like, huh, more likely to play if he plays. So here we go. On to the next question. Who's in the lead right here? In the lead right here, we have Bright Ant, Epic Dolphin, Proud Bobcat, Lively Alpaca, and Adorable Rabbit. Well, you know who I'm voting for. I'm voting for Adorable Rabbit. You got this spooky, adorable rabbit. Oh, you blinked your eyes. That's crazy. Here we go. Next question. Two events that have no influence on the probability of each other are completely what of each other. I'll kind of hop out of the way, but I feel like you should get this very quickly because we've been reviewing it. Make sure to pay attention between these in-between sections right there because that's when I usually give hints to a lot of the questions. I'm not saying that's the answer. I mean, you got two events that are completely have no influence on each other. Like knowing one would tell you nothing about the other. Disappear off screen. Knowing one would tell you nothing about the other. Oh my gosh. We gotta throw 1,000 points right there. And don't worry if you got it wrong. I bet it was a misclick. I want to say a huge thank you because this is what we're here to do. We're here to review. So when you see it, you're like, two events that have no influence on the probability of each other are completely independent. And then if they are independent, we can easily what those events together. Now we go to the formula sheet and we say if they are independent, remember you do get this sheet. So you look at it here and you say, well, if they are independent, I can easily what those events together. So if we want to multiply things, we need to check if they're independent. Great job, Hannah, right there, and Sarah. If we want to multiply things, we have to check to see if they're independent. And if they are, we can easily multiply them together. There are ways to multiply when they're not independent, but it gets complicated quickly. And there is ways to add if they're not disjoint, and it gets a little more complicated. Won't be that way on the test, though. So really amazing work. When we get all right answers, we go on quickly here to the leaderboard. Adorable Rabbit in third place. I wish the leaderboard was still animated. Is there not like animated leaderboard? Animated leaderboard. Don't end the Kahoot. Bitmoji, what's that? I don't know. Oh, player identified. Know that. Wow, that's kind of cool. I'll close the Kahoot. Oh, here we go. Next question. Question number 3. To multiply the probability of A and B, the two events must be what? Review, review, review. Should be easier questions. Look at the formula sheet while doing this. All you have to do is glance at the formula sheet and you will see the answer. So if you see things like this on the test, you are going to look where, if you've already typed your answer, tell me in the chat. If you see a question like this on the test where it's like, to multiply the probability of A and B, the two events must be what? Where are you going to go look? Where are you going to go look? The formula sheet. Cameron knows right there, and so does Jameson and Hannah and Tyler right there. Great job. We're going to go look at the formula sheet, because the formula sheet's going to have probably a lot of things that are going to help. And we did pretty well. You see, don't worry. We did pretty well. We're more on track right now. We didn't get that almost perfect like we did last time. But to multiply two things, you're looking at this right here. I'm going to disappear right after I highlight it. Does everyone see right here? Why does it keep wanting to highlight that? Weird. That line right here, the probability of A and B is found by multiplying A and B, and the two things must be what? So repeat it in the chat, just to make it clear. Don't worry if you got it wrong. This is the time to repeat it and learn it. Even say it out loud. Like, if you say these things, I want to point this out. The reason I have you chant things, great job right there from She's King. I love that. Because writing it in the chat is one thing. Talking it through is another thing. Thinking it's another thing. We have to learn multiple ways. We have to learn by repetition. That's why I say things like 50 times, like, Brian, I know it. Well, good, then we've learned it. But we're still here to practice and help everyone know it. So when we think about multiplying two things, like if I ask you, what is the problem? You ever play that McDonald's, you ever get a McDonald's large fry and it's got Monopoly on it and you're like, oh my gosh, I want a large fry. Oh man, I want a Big Mac. You ever play that? You ever play that? So if we were to come up with a question and say something like, McDonald's has the following probability on the Monopoly. We only talk about games here, or food. Monopoly. Probability of Big Mac is equal to 2%. Probability of large fry is equal to 10%. The probability of soda is equal to 5%. That's what you get. Those are the following probabilities. Your meal had 3 tickets on it. What is the probability with this meal you can get a full meal, i.e. Big Mac, large fry, and this? And to be specific, we should probably say it this way. What is the probability? What is the probability when you pull the tickets, you get Big Mac, large fry, in that order? Because it could get complicated a lot faster. Think about this. What's the probability you get a Big Mac, and then you get a large fry, and then you get a soda? So you're just saying the first one's a Big Mac, probability of that, and then the next one's a large fry, probability of that, and then the next one, exactly, I think that's it. It's a 1 in 10,000 chance. 1 in 10,000. And then I think it's about a 1 in 5,000. We have to look at the permutations of the ways it can occur to think even more advanced on this problem, but it can get more complicated quickly. I'm not going to do the more complicated versions of this, like, well, then how many ways could this occur, which is permutations. There's more to probability than we've learned. But this one way right here where you get a Big Mac first, and then, because when we're multiplying, what word do we use to multiply? And great job, everyone in the chat. What word do we use to multiply? And look at the cheat sheet, no, the formula sheet, not a cheat sheet, but what word do we use to multiply? And that's when you're saying you get a Big Mac, and then you get a large fry, and then you get a soda. Now, what do we mean by independent? We mean when you pull that ticket, that first ticket, McDonald's has changed it up, and I've lost my pen for a half second. Now you've got 3 tickets right here left. Each ticket is what? When I pull this ticket right here, what I get on it will be completely what of the next ticket? What I get on the first ticket will be completely what of the next ticket? Exactly, Hannah said it perfectly. And Hannah, great job, that's a perfect answer, because each ticket does not influence the next ticket. It's not like I pull this ticket right here and the next ticket's like, he already won, so I'm going to change from being a winning ticket to a losing ticket. And so if these are random tickets, they would be completely independent of the other ones winning and losing. So if I win on the first, the probability of large fry is still the same for the second, because winning on the first does not influence the probability of the second. Does that make sense right there? How we talk about things being independent, we can multiply, see the probability of this, and then this occurring. You can create a longer chain of things occurring. Like, what's the probability you win 3 Big Macs in a row? Ooh, let's do a few quick tough ones here. What is the probability of winning 3 Big Macs in a row? What's the probability you get a Big Mac and a Big Mac and a Big Mac? It's like, hey, I want all my Big Macs now. They're like, I'm moving the decimals in my head. That's all it is. Henry, great job right there. Henry points in the chats. And I think that's it. It's all, you gotta be careful with the zeros right there, but it's basically 0.02 to the third power. But now here's a more complicated one. Great job, points in the chat. What is the probability of winning at least 1 Big Mac? Gotta capitalize that proper word, whatever it is. What's the probability of winning at least 1 Big Mac? I know the math. I'm trying to think what it would be. I can't, no. I think it's gonna be about 8%. Maybe 6 or 7%. You got 3 tickets. What's the probability you win at least 1 Big Mac? I think it's about 6%. I'm gonna guess 6% off the top of my head. Nah, there, it's close to 6%, okay. About 6%. And very close, Hannah, very close. Just change a little tiny bit of the math. You're right there with the equation. So here's what we have to write. This is a good one to practice if you haven't done it in a while. You have to write everything that can occur is you will either get at least 1 Big Mac or what? This is the sentence you have to write if you remember back from this chapter. You will either get at least 1 Big Mac or what? Great job, Sarah. Yep, Sophie, this is how I do it right here. You will either get at least 1 Big Mac or no Big Macs. Does that make sense? What is the probability of not winning a Big Mac? Probability of not a Big Mac is what? Which is the complement rule right here. What is the probability of not a Big Mac? Just with one. You pull 1 ticket and it's not a Big Mac. You got 2% chance of winning a Big Mac. Probability of not Big Mac is this. So now we rework our equation, and the reworking of the equation solves mathematically for this right here, because we want to find at least 1 Big Mac, so we're just going to subtract this off on the other side, and it'll become a negative like this. So to find the probability of at least 1 Big Mac, we're first going to have to find the probability of getting no Big Macs when we choose 3 Big Macs. So what's the probability the first one is not a Big Mac, and the second one is not a Big Mac, and the third one? I think Hannah sees it now. What's the probability the first is not a Big Mac, and the second is not a Big Mac, and the third is not a Big Mac? And you're hearing the words. The first is not a Big Mac, and the second is not a Big Mac, and the third is not a Big Mac. What is the probability there? The first is not a Big Mac, exactly 0.98 cubed, because it's just the probability of a Big Mac, not a Big Mac, not a Big Mac, not a Big Mac, which is the probability of no Big Macs, and thus the equation is this right here, 0.98 raised, oh my god, what are we doing? 0.98 raised to the third power, and that is equal to 0.0588, I believe. Yep, I think we saw in the chat earlier, and that's how to do it. Good, tough problem right there. We like the tricky ones. A little bit of review of mathematics and probability on how to do those. Heading back over here to the quiz. Let's do it up. Leaderboard time. Bright Ant, Epic Dolphin, Adorable Rabbit. You're in third, but you got this. Oh my god, Mubot. Is a Mubot here? Mubot's somewhere. Continue on to the next question. Let's do it. The probability of a gross jelly bean is 25%. If you eat 3 jelly beans, what's the probability? They're all good. So a gross jelly bean has a 25% probability. What's the probability of a good jelly bean? What's the probability of a good jelly bean? What is the probability? What is the probability? Wait, darn it. There we go. Mubot got mad. I typed for Mubot and he was mad. Mubot's going to do his own thing. We're trying to get Mubot animated. We're working on that in the background. So So what's the probability in the chat of a good jelly bean? If a gross jelly bean is 25%, what's the probability of a good jelly bean? Jelly beans are either good or gross. So you're gonna pull out of those bags, you know, those, what are they called? The Harry Potter jelly beans, the ones that are really scary. Sometimes they're really gross, sometimes they're really good. 75% chance of good. 3 out of 4 are good. So now right here, I think we got it. Nice job, Emma. Emma's just wow. We're gonna replace the pinned message with that. That is all the mathematics in the answer. Emma first did 1 minus the probability of gross to find the probability of good. So it's either good or gross. That's all we're going for. They're compliments because you either like it or you don't like the jelly bean. Like, don't like, compliments. And bean boozled, bamboozled, bean boozled, bean boozled. I like that all right there. And then once you find the probability of a good jelly bean, think about this. You eat your first jelly bean and it's what? So say it with me. I ate my first jelly bean and it was what word? What's the probability they're all good? So I ate my first jelly bean and it was probability they're all good. First jelly bean was good. Now what word? Because we're about to multiply. We're going to say a 3-letter A word next. I ate my first jelly bean. It was good. And the second jelly bean was good. And the third jelly bean was good. Now what does it mean that they're independent? When you eat your first jelly bean, and this is a big bag of Bean Boozled, a huge bag that doesn't change probabilities. The second jelly bean doesn't care about that first jelly bean. The second jelly bean is going to have the same good or bad nature, whether or not the first jelly bean was good, meaning that each jelly bean is what of previous jelly beans being eaten. Each jelly bean is completely what of the previous jelly bean that you ate. Like you pick up some jelly beans, they're all completely what of each other. They're not going to change to be good or bad. Exactly, they're independent. Because when you eat a jelly bean, does the other jelly bean become gross all of a sudden? I guess, like, here's the thing. You'll know where I'm going with this. How does orange juice taste? Is there ever something you do that maybe changes the taste of orange juice and you would say, well, orange juice and how it tastes kind of depends on if you just did this. You know what I'm talking about? Toothpaste, right? Oh, this orange juice is so gross, I just did it. So that would be a dependent relationship. You'd say then, like probability you brush your teeth, probability you like orange juice. Well, if you just brushed your teeth, the probability of liking orange juice is going to go down. So does that make sense why that's dependent? Like the like and dislike of orange juice depends whether or not someone brushed their teeth. But the like or dislike of a jelly bean, I think it's pretty independent of the previous jelly bean you just ate. I was trying to think, when would this change? I'm always trying to outthink the questions too. Someone's like, well, what if we just had like a cherry jelly bean and I don't want to have cherry lime? Sure, we could, you might be able to somehow outthink our questions, but try not to, unless you're me. Let's go back over that leaderboard. Bright Ant, where you at, Bunny? Bunny, no. I want to put Morty on a green screen and film him and then have him run around here. Like I could just have a green screen to Morty. It's kind of been one of the things I've thought about. Maybe I'll tell Chelsea this week. I'll be like, I've got a green screen blanket, so I should be like, let's do it. And then I could just be like, Morty, and he could just run through the screen. I'd have to get him like running across. It'd have to be like right angles and stuff. All right, continuing on. The probability of getting a multiple choice question correct is 80%. With 5 questions, what is the probability you get at least one wrong? At least one wrong. So what are the 2 things that would occur? You'll either get at least one wrong, or you'll get what? So write your sentence right now. You will either get at least one wrong. So 1 equals at least one wrong, or what? What's the rest of that sentence? So I think people are solving it, and then we'll start to see some, or none wrong. Oh, great job, Carrington. So you'll either get at least one wrong, or none wrong, right? We're putting in the chat. You'll either get at least one wrong or none wrong. So remember, we want to find at least one wrong. So here's the equation you need to solve. We're just going to take at least one wrong, bring it to the other side. Or excuse me, not at least one wrong. We're going to bring over none wrong. So what are you going to have to solve for? Look at the chat right there to figure out this probability. You have to do 1 minus something. In the message right now. There it is in the chat. Because you'll either get at least one wrong or you'll get none wrong. And that's why that adds up to 1, because they're complements. Like, I'm either going to get at least one of these questions wrong or I'll get none of them wrong. You have to find the probability of getting none wrong. None wrong, because that would be getting them all right, is 0.8. And you're taking 5 questions, 0.8 to the 5th power, 1 minus 0.8 to the 5th power. Great job, Emma, right there. Yep. That's pretty good. I gotta throw some points on this. Who feels like these problems make more sense when you write your sentences? Please check out this format we use to solve these when we get to an at least one problem. I think the writing of the sentence, Abigail said right there, thank you, Abigail. I think when you write the sentence and you say, okay, here's everything that can occur. Either I'm gonna get at least one wrong or I'm gonna get them all right. Like you got a test in front of you. Well, I'm either gonna get at least one of these questions wrong, one or more questions wrong, or I'm gonna get them all right. So what's the probability? And let's write this down here on paper so people can see. This is how to conquer the at least one problems. We have right here a multiple choice. Why was it point? Carrington, let's answer the question. So here, let's solve this and do a different version too. So probability of getting a question right is 80%. You take 5 questions. What is the probability you get at least one wrong? And so with this right here, the probability, and so we have 1, which is everything that could occur, is either going to be at least one wrong, or, and that's an or right there because it's a plus, this means they're disjoint, they both can't occur, you can't get at least one wrong, and you can't get none wrong. None wrong. So this is why Carrington right here, then we'll look at what the other one is. When you say none wrong, what does that mean you did on the test? If you got none wrong, what did you do on the test? If you got none wrong, what did you do on the test? So if you got them all right. So you can find out the probability of getting everything right, and that means you got the first one right, and you got the second one right, and you got the third one right, and the fourth one right, and the fifth one right, which long form is going to be 0.8 times 0.8 times 0.8 times 0.8, 5 times, and so this right here. But what is the other, what is this going to find if we do this? And Carrington, thank you so much. Let's start with Carrington, some big points right here. What is that going to find? Like this equation finds the probability of getting what? Which you can kind of think through that. What does that equation find? It's everything but getting them all wrong. At least one right. Does that make sense? Like if you read this, I sometimes read this as everything, which is 100%. Everything, and then but is minus. Everything but getting all the questions wrong. Does that make sense? Like what is an event that is everything but getting all the questions wrong? Well, if everything but getting them all wrong is at least one right. I think when you can read it more as a sentence and read everything but getting them all wrong, because 0.2 to the 5th power is you got the first wrong and the second wrong and the third wrong and the fourth wrong and the fifth wrong. So everything but that would mean an instance where you got at least one right. So good questions right there and good practice. Thank you, Carrington, for bringing that up. Figuring out which one of those to use, the 0.8 or the 0.2, can be confusing. You get a 50-50 shot if you just kind of guess at it. So if you don't know how to do it and you're stuck, you could just guess one of those. And then you might be right. There's some tricky ones on the test, but you probably have a 50-50 shot if you use those techniques on the at least one. So even just knowing the technique, you could do it. Winged boa, elated squid, silly sphinx, and lovely alpaca bright ant. Good to see you there. Next question. What is the first thing we need to do when solving a sampling distribution problem? Oh my gosh, he's going to have to appear here in a second. What is the first thing we need to do? He appeared at the start. Oh no, I should be very nice. I think I'm trying to remember which answer I put. Oh, I'm about to be scared here. Because, yeah, I would do this first. I would do this first. I would do this first. I would totally do this first. I'm glad he appeared at the start. I'm trying to remember what I put as the answer. Yeah, I would do this first. At 100, someone's gonna be like, no, you say to do this all the time, but no, I do this first. Come on, past Brian. Yes, yes, yes. He appeared at the start. Let me tell you why. If you got this wrong, it better be square. It better be square. What's square? Marking notation is huge. But let me tell you why. Why do you think I'd figure out if it's cat or quant first? And I do mean this. So don't worry if you got this wrong. Don't worry, the code's for fun. Why would you figure out if it's cat or quant first? Why would you figure out if it's cat or quant first? Why would you figure out if it's cat or quant first? Boom, Sarah. Sarah, you know what we're doing? We're doing one last. We did this one time in class, but Sarah sees it right there. Don't tell anyone I did this, but we did it one time in class. We're doing it right here too for all the Kahoot followers right there. Remember that cat and quant, cat and quant guide the notation. Very important thing. Because when you pick if it's categorical, when you pick if it's quantitative, it is going to guide the notation. So anytime you see sampling distribution, who do I want you to think of? Anytime you see sampling distribution, who do I want you to think of? I don't think it's going to work. What happened to my thing? Who do I want you to think of? There we go.
Think of me. Wait, why is my head not moving? There we go. I'm a cat named Quan. Yeah! Perfect. Remember me, cat named Quan.
Okay, we'll just keep him that big and that crazy on the screen from now on. Okay, back here to the main screen. Let's go do it. Okay. I hope everyone has as much fun as I do. Okay, cat named Quant, because if it's categorical, here's the thing. And so, you know, maybe listen in a little bit here. The sampling distribution of the sample proportion has the what as its mean. The sampling distribution of the sample proportion has the what as its mean. The sampling distribution, or the sampling distribution of the sample proportion has the what as the mean. The sampling distribution of the sample proportion, and Abigail said right there, P. This stands for the mean of the sampling distribution of the sample proportion. That's what I'm asking you about. I'm asking you, what is that? Well, that is that, but that's not what we're looking for. We're looking for that. And what does that mean? If 20% of students love Taco Bell, and I took a sample, I'd expect to see 20% of students love Taco Bell. And it's the true proportion. Exactly, Cameron, right there. Cameron, great work right there. It's the true proportion. What is, well, see if I ask the next one's kind of obvious. What is the mean for the distribution of the sample mean? What is the mean for the distribution of the sample mean? So you go here and you look for a mean. Here's the means of the distribution of the sample mean. It is mu, mu, mu. So it's mu. What is a question I could know data on where I would know the true mean? Like MuBot, exactly. Our channel mu2. Mu2 is in the symbol for our channel. What question would I ask students to know, or like if I knew the data on it, I would know the true mean and stuff like that. So it'd be the sampling distribution of the sample mean. Like Brian goes out and talks to 100 students where he knows the truth of the blank. I'd have to know the truth. So that's what the mu is. It's the true mean. Like, especially with students, what would we know the truth on? Like Brian goes out and talks to 100 students from a population where the blank is blank. The true mean is what? The true mean of what? So think of some quantitative questions. What would we know? Brian goes out and talks to 100 students where the true mean what? What would GPA or what would UT probably know? Well, out of state, but good answer, Sophie, right there. We're going to throw you some. We might know the age of students at UT. Brian knows the true age of UT students. And we could know out of state. And out of state would be sampling distribution of sample proportion or sampling distribution of sample mean. Would out of state be sampling distribution of sample proportion or sample mean? And this is the first thing you do is you say, okay, this question asks about in-state, out-of-state. Are we doing proportions or means? Proportions because it's categorical. So that's the categorical right there. That's why we say cat or quant, because this is categorical, this is quant. If you're wondering all of our things right here, we talk about the cat named quant because categorical is proportions, quantitative is means, like a quantity, like how tall are you, is going to be the mean height of people, where categories lead to proportions, like the proportion of people who are in state, because categorical, in state, out of state. So the questions would be like, Brian's trying to figure out what % of units are defective. Would that be proportions or means? Would that, Brian's trying to figure out, and he knows from a supplier that they have a certain amount defective. I said amount, but there's 80 defective per 1,000 for this supplier's thing. Is that proportions or categorical or quantitative? It's proportions. Defective, not defective. Even though I'm saying numbers, you're like, but you're saying numbers. You're saying like 80 are defective. Well, the thing is the question is it defective is categorical. Where we could say like the cost of repair would be what? So if the question said, we are trying to figure out if the cost of repairs have been unusually high, the company reports a mean for all their, a mean and standard deviation, that would be quant, because cost of repairs is quantitative. So that's the first thing you want to do, and people said it correctly. I know this was a question that some people maybe lost their streak on, but when you start one of these sampling distribution questions, look, is it cat or quant, and then go to the where. Look if it's cat or quant. This is the steps. Start a question. Is it cat or quant? Okay, it's cat. And then you go where? To the notation. Go to the notation, to the formula sheet, and then start marking it. Don't immediately start marking notation because you might get it wrong. I mean, you could mark notation if you're that good. You might be. So maybe the all-stars right there are ready to jump into the notation, but I would say determine cat or quant, then mark notation. Here we go with the next question. Let's do it. We got Bright Ant, Lively Alpaca, and Silly Sphinx in the lead right there, with Charming Ferret and Lovely Badger coming up behind. When trying jelly beans, if you take 2 jelly beans, what is the sample space of good and bad jelly beans that can occur? Sample space is every combination of possible outcomes, also including the order in which they occur. Sample space is all the possible outcomes, also including the order in which they can occur. So this is not sample frame, it's sample space. So you could get a bad and a bad jelly bean. You could get a good and a bad jelly bean. You could get a bad and a good jelly bean, or you could get a good and a good jelly bean. The sample space is everything that can occur, and that's a good definition to have, and great job right there. So sample space is everything that can occur, but be careful, we do have sample frame. Sample frame, when it comes to sampling, is everyone we could theoretically sample. Like if Brian goes out and hangs around campus and talks to students, his sample frame would be students, what? Would it be all students? Brian goes out today and talks to students on campus. My sample frame would be what? This is a sample frame question now. Brian goes out and talks to students around campus today. His sample frame is going to be what? What is my sample frame? Students on campus today, exactly. I can only talk to students who pass me, right? Students in that area in Brian's vicinity. Now, that doesn't mean I'm going to sample them. I might be like, hey, I'd like to give you a survey. And they're like, nope. And I'm like, oh, some non-response bias. So students on campus, I love students on campus. And so it'd be students in the vicinity of Brian who he could possibly speak to. Like we get that specific. And then the population would be students. And then the sample would be the students who talk to me. So remember, population is the big one. Then you have sample frame. Then you have sample. So it goes population, everything you're interested in. Sample frame, everything you have access to sample, and sample, and convenience sampling, and then Brian is pretty much doing a convenience sample, which is not a good random sampling method. So is sample space can be the population, but is Brian getting a good sample space by walking outside today and talking to students? Is that a good representative view of the population of UT students today on a Friday? Midday Friday, is that your general, like, is that a good random sample of UT students? No, we didn't yet. We haven't got any copyright claims. One class I played it for like 30 seconds a long time ago, and that's when we got hit. And then I got brave enough to do it again, and we haven't been hit. Maybe Monster Cat is nice now, but they haven't copyright claimed me since. So sample frame is everything you can sample. So the sample frame is everything you have access to. The sample space is when it comes to probability chapter 12. The sample space is all the combinations of outcomes that can occur. But it's different chapters. They just both use sample right there, but sample space is not for sampling really. I mean, I guess it kind of is, but it's more for like if you're flipping a coin, what's the sample space of flipping a coin? Just a single flip of a coin. Like the sample space is the possible outcomes of things that could occur. The sample space. So what's the outcomes of flipping a coin? Heads and tails. That's the sample space of flipping a coin. When the Democratic National Convention does a poll to figure out what Democrats want at their convention, what is their sample space? If they're trying to understand Democrats and they speak to people at the convention, what is the sample space? The Democratic National Convention does a poll of Democrats at their convention. What would be the sample space? The sample space is sample frame. Oh my gosh, see, even I'm not. Sample frame, sample frame, sample frame. The Democratic National Convention does a poll of people at the convention to figure out what Democrats want. What is their sample frame? And I actually said right there, Democrats at the convention. Because those are the ones they have what to. Those are the people they have what to. Think of the A word, about 6, 7 letters. Those are the people, I think it's 6 letters. Those are the people they have access to. Those are the people they can sample. The sample frame is everything you can sample. Does that make sense? And so they might want to understand all Democrats. Not the best view. You go to Republican National Convention, anything like that, it's not purely representative of the whole of a party then. But so that might not, it might be a little biased towards the kind of the most active in the party. And then your sample would be people what at the convention. Not everyone at the convention, because you could probably theoretically speak to anyone at the convention. So the convention is your sample frame, because you're withdrawing from that frame or pulling things from the frame. But the sample is going to be what? The sample is going to be what? The sample is going to be what? Those who talk to you, exactly. Those who talk to you. So the sample frame, like if you do a census, then you collect everything on the population, and your population, sample frame, and sample are all the same sizes. And that's the only way you get something to be equal population, equal sample frame, equal sample. Only when you do a census, which is collecting data on the full population of interest. Okay, who's in the lead? Bright ant, lively alpaca, silly sphinx, charming ferret, and lovely badger. Next question, let's do it. What 3 values will you have to write interpretations for on test number 2 worth 12 points? What 3 things do you need to write interpretations for? Is it the root mean squared error, the standard error, the variance inflation factor? Is it the multiplication addition complement rule? Is it the QQ straight enough, no outliers, plot doesn't thicken? Or when we get to regression, are there 3 interpretations you need to know? 3 interpretations you need to know, known as the R squared, which is the percent of variations explained in Y, explained by X, percent of variation in Y explained by X. The slope for each 1 unit increase in Y, X is, oh my gosh. The slope for each 1 unit increase in X, Y is expected to increase by B1 on average. And the intercept when X is equal to 0, we expect Y to equal B0. Now, if I said those a little bit quickly, I've got some good advice. 1, I would definitely go, what notes do I have up currently? Has anyone been watching the speedrun videos? Has anyone been watching speedrun videos? Anybody? Bueller? Winging. I don't think we have interpretations up. Bueller. Watch the speedrun videos. I'll probably go grab a speedrun video. R squared is not correlation, little tips like this right here. And let me go grab speedrun videos and drop them in here in the chat. Or if you just go to review 2, review 2 has the speedrun videos, and you will see me go through these. Now, here's the thing. You can hear me say these interpretations 50 times, but you're probably not going to learn them until you what, or try to what to someone else. You're not really going to learn these interpretations until you what? Like, you can hear me say them a billion times. You got to practice them. You got to write them down. You got to say them out loud. You got to explain them to someone else. You have to be able to walk someone through them. Because I can do them all. I've done this a while. Look at that R squared right there. Blank percent of the variation Y explained by the variation X. If you haven't seen these videos either, oh my, well, you can hear that too. A little loud for me. So these are the more classic videos right here. I go through explain residual plots. Here's the output. When X is equal to 0, we expect Y to equal B0 on average. For each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. And blank percent of the variation Y is explained by the variation X. Those are more classic videos. You've got test question review videos. And then over here, you have the more fun review videos.
Epic Stat Tool 1 speedruns of statistics. Brian Stevens versus Chapter 7, Linear Regression. Begin.
Let's start with the conditions.
So calm. Let's start with the conditions for. So QQ straight enough, no outliers, plot doesn't thicken. Going through residual plots, going through the interpretation, see if you can do it yourself. Once again, I totally mean this. You can hear me say it a million times, but I promise you on the test, you're going to write out 3 interpretations if you want. I mean, you don't got it. You can just not do it. but the test will be a higher grade if you do it and you know how to do it. So B0 is the intercept and B1 is the slope and X is the X variable. Thank you, Cameron, right there. I did like 3 or 4 takes on some of these and I would mess up because it was a one-take thing. And I'd be like, blah, blah, blah. And I was like, dang it, because I'll like personally mess up a take if I get it wrong, and then sometimes I'll go back in and edit it, and you'll see me just kind of like blur a little bit. You have on your, oh yeah, because I was like, I gotta be exact, no jokes, serious time. So sometimes people say, Brian, you're not serious enough, and you can go to what I'm covering right there, the interpretations, illogical intercepts. Like when someone has a weight equal to 0, we expect their height to be equal to 50 on average. That wouldn't make sense. Use plug-in 0 for weight. There's residuals. There's residual plots, all this stuff right here. Great stuff, finding R squared from R, all these important things. Serious face on, check this out, check out the review videos, always great. And my last little tip for you is this. I think we have some of it up. Do we have some of it up? Some of it up? If you want, what do we already have posted? What do we already have posted? This is one. What do we already have posted? We already have posted exam 3 review. And do you remember what I told you? If you're in my class, I talked to you about, oh my God, I'm wearing the same shirt from 4 years ago. It's one of my favorite shirts. Exam 3 is posted. You've learned nothing of exam 3 yet. But what if I asked you the first condition for the confidence interval for the mean? Or the first condition for the confidence interval for the true proportion? Or the first condition to test the mean? Or the first condition, Cameron's got it right there, watch them before class to get a preview of what's going to happen. What if I asked you the first condition? The first condition for the confidence interval for the mean. The first condition, use your knowledge of what we've been practicing in chapter 13, 14. For the first condition, what do you think it is? How in the world would you know that for all these tests that we haven't done? Ignore that last thing. What do you think the second condition is? The second condition, this is chapter 13, 14 we're reviewing right now. This is test 3. We will do the same sorts of things. Next condition is 10%, sample less than 10% of the population. And then you what? I don't know if I wrote it on here. I should have wrote it. But be very careful. What do? You put them in the chat. I mean, I'm doing a long one right here. I don't know this. I might not have been teaching it the same way back then. It looks like I wasn't. But I would do what? I would pause. And you see, if you notice, there's going to be different ones later on, like the nearly normal, which is kind of like the large enough n condition. And there could be a fourth condition. But right here, before you do this, you pause because the next condition or next two kind of depend on what you're doing. But you can always say random and 10%. Be careful. Regression is QQ straight enough, no outliers, plot doesn't thicken. But check out these videos. I do think they're great help. And then try to write them down as you're watching. Just do them in little bits. Don't try to study all day. Be like, I'm going to take 30 minutes. I'm going to write down notes. And then I'm going to repeat it back. I'm going to say it out loud. It helps your brain activate on these things. With that, let's go back to the Kahoot. And thank you so much, everyone, for all this positivity. Here we go with the next one. Little bits. Little bits. What is the interpretation of the slope? It might just how I did it. Type it in the chat. Get some points. Just click there really quick. Type it in the chat. Can you type it? I'll throw 10,000 points for the first person to type it. See if you can do it. Do it in the blank interpretation. What is the interpretation of the slope? I think it's a circle. No. Oh, that's a circle. See, we lose people. They're not playing. For every 1 unit increase in X, we expect Y to increase by B1 average. Jameson, boom, right there. Got it. That's exactly it. That easy, that quick. If you know how to do that on the test, you're really good. You're good to go. And so when you think about this right here, if we have something like hours studied, so if we were to look at hours studied on the test, and then we were to look at exam grade, and we go right here, some random data. Okay. Why does hours go into X Why does hours go into X? 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 Because it explains, like, how long you study for the test probably explains why you get a certain grade. You think, like, what is the explanatory variable? What is the explainer here? And X's explain why something is happening. Maybe your hours explain why you got a certain grade. So if you look right here, what do you think a little QQ straight? What do you think Brian's looking at this and thinking, what is the minor issue I see to this? I don't think it's that big. I wouldn't love this as a test question, but I'm thinking maybe a little issue with what? Maybe there's a little issue with the second one too. Little curvature, right? Little curvature. This is probably straight enough. We would put something more bendy, but when you do your QQ, two quantitative variables, straight enough. A straight line goes through the data, and we'll see it better if we plot the line on it. So let's go here to fit line. Yeah, you really see it right. Let me zoom out, or let me bring it down a little bit. You really see it right in here. You see how the points kind of curve around it? It's iffy. And if we go statistically speaking, the answer statistically is it's not straight enough. The null hypothesis for this test is that it's straight enough, and we actually reject the null and have evidence it's not straight enough. This one I would not love as a test question, though. Let's examine those residuals, though. I don't think is a great test question. Like, it's an iffy one, and p-value is 0.02-ish right there. That's the p-value to check to see if it's linear enough. We don't do that in 201. We don't do that here. We don't do lack of fits on this. But how about we look to see if the plot is thickening? Brian, and write this down, go make a what? Let's go see. Yeah, I love that quote. Let's go make a what plot to see if the plot is thickening. The fourth condition, QQ straight enough, no outliers, plot doesn't thicken. Let's go make a what? A residual plot. So we're going to go right here and go to plot residuals. Where's plot residuals? Plot residuals. And I mean, now you notice what's easier to see. What's easier to see now in this? Boop, 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 boop. Oh, I got to go like do. There's a little bit of plot thickening. It might be due to more data, a little plot thickening, but I really see the curvature more. It might have some thickening. We'll try to make it obvious. There's also, you can do a test for this, but I'd try to make it more obvious. What is the estimate of the intercept? What is the estimate of the intercept? What is the estimate of the intercept? What is it? 40.69. It's right up there. That's the estimate of the intercept. You also see it in the equation B0. How many x's does B0 have next to it? Just think B0. How many x's does B0 have next to it? Like B1 has one x next to it. Like this, that right there, that's B1, and it has one x next to it. B0 is when x is equal to 0, and it doesn't have any x's next to it. So it's just B0 when x is equal to 0. And then down here, the estimate of the slope is 6.7, and that's next to hours, which is the x variable of interest, or the x variable. And so what does this mean? Interpret the intercept, interpret the slope, interpret the r squared. This is 12 points of your test. So try to do those three things right here, right now. Interpret the intercept, interpret the r squared, interpret the slope. If you can do that, I'll tell you how good you do. Let's practice this right here. Interpret the intercept, interpret the slope, interpret the r squared. Try any of those. R squared is right there. And so read the chat. Try to do this. If you can do it for this question, you can probably do it for others. So can you do it for this question? What would it be? Try doing these. If you can do these now, probably pretty good. What would they be? What would they be? For every additional hour studied, we would expect an increase of 6.735% on exam grade. Correct, and that's because exam grade is in percent, or we could say points. And so Sarah, great job right there. It won't always be percent, which you're just doing that because it's exam grade. I'm just making sure someone for the test doesn't write percent for each thing. But that is correct. 91.3% of the variation in exam grade is explained by the variation in hours studied. Blank percent of the variation in y is explained by the variation in x. Boom, got it right there. Great job, Sophie. And then all we're missing is the intercept, which is logical. It's a little bit of an extrapolation. Extrapolation means you're going outside the x bounds of the model. So the intercept, which is going to be over here, the intercept is right here. There's the intercept. What is the intercept? Well, how do we interpret it? When hours studied is 0, we can predict the exam grade will be 40.692 on average. Great job, Sophie and Ashlyn. Let's make Ashlyn a mod over here. Thank you, Ashlyn. Adding you as a mod. Great job right there. For every 1 increase in hours studied, oh, I added a mod so I can't see the thing. We expect the exam grade to increase by 6.753% on average. And remember, it's because it's exams. Won't always be percents, but we can say the score or the percent. So great job for hours studied 0. You can expect a 40.692 grade. Probably sprinkle on a little on average. Personally, and so Lily, great work right there. My graders sometimes want the on average in there. It's not that big of a deal. Like if you say expect, you just don't want to say things like will, like a student will score this. We have a saying right here, will. Here, we'll do the Mubot thing because he knows about will. I should just make it will. But he says, what does he say? Will, you will lose points. Unless your name is Will, then you're awesome. But don't say it will be this or will increase by this. It's expected, predicted on average. So that gives some like, well, here's what we expect to see. Here's what we think will happen. Not what will happen because it's not cause and effect. Good work right there and good practice. Remember, if you can write it down here, you're more likely to be able to write it down for the test. So probably another easy one if I remember my questions. Bright ant, lively alpaca, silly sphinx, elated squid, and inspired iguana. Next question, let's go. What is the interpretation of the intercept? Try to say it 3 times out loud. When x is equal to 0, we expect y to equal b0 on average. When x is equal to 0, we expect y to equal b0 on average. When x is equal to 0, we expect y to equal b0 on average. So for equations, it could be like when somebody's height is equal to 0, we expect their weight to be equal to -50 on average. But that doesn't make sense because you can't have a height of 0 and you can't have a weight equal to -50. When someone's hours studied is equal to 0, we expect their grade on the test to be 40.69 on average, which does make sense because it's not illogical to study 0 hours, even though it's a slight extrapolation of the model. Good work right there. Oh my gosh, I walked away and the green screen got mad. I was walking around a little bit because I can walk around now. On the last alias, the grader took off a full point of it because I didn't say on average. Should I email you? Yes, you definitely should, and I'll give the points back. I have a lot of points to give back, but you can, and I will give back points. When x is equal to 0, expect y to equal b0 on average. Just boom like that. And notice, when you say the intercept, you say 0 how many times? So listen carefully. When x is equal to 0, we expect y to equal b0 on average. So when you say the intercept interpretation, you say 0 how many times? Say it twice. How about the slope? For each 1 unit increase in x, we expect y to increase by b1 on average. Does everyone hear that? Just like be like, whoa, wait a minute.
Wow.
For each 1 unit increase in x, we expect y to increase by b1 on average. Never. Cameron's like, wait a minute. It's a way to remember it. When x is equal to 0, we expect y to equal b0 on average. For each 1 unit increase in x, we expect y to increase by b1 on average. Notice you also go from x to y. Same thing with, the only one that breaks that is r squared. Blank percent of the variation in y is explained by x. So remember, explained by x. I love the emojis, Cameron. I wish I could have Mubot doing them, but he won't do those. Next question, here we go. Great job, bright ant, lively alpaca, silly sphinx, inspired iguana, and elated squid. Here we go. What is the interpretation of r squared? Type it in the chat for practice, but click the button quick if you're still here. Remember, we got Kahoot t-shirts. Where'd my Kahoot shirts go? Oh, I got them over here. People are so excited. Thank you, Kahoot, once again for giving us these Kahoot t-shirts. And last time, I had to pay for Kahoot. Oh, you just told me to walk away. Last time I had to pay for Kahoot, and Kahoot refunded me because we were able to get it through UT. Thank you, UT, also. Rosie Sasso and a bunch of great people at OIT for helping out. So we got Kahoot t-shirts. Very much. Blank percent of the variation y is explained by the variation in x. Blank percent of the variation in y is explained by the variation in x. And finish my sentence. R squared is not this word for 10,000 points. R squared is not this word. You don't. R squared is not this idea. It's not correlation. And let's go look at that right here. R squared is not correlation. R squared can be found by taking correlation and whatting it. R squared can be found by taking correlation and whatting it. Squaring it. So let's look right here. We had a cheeseburger eating contest. So do cheeseburgers explain your exam grade? Perfect. I love it. I'm so happy with my ability to make random data. Okay. Now it looks like something's going on right here, because interpret that this is how many cheeseburgers you ate the night before the test. Interpret this right here. Interpret the R squared. Round it to 1 decimal if you want, or to a percent. Interpret that R squared, which is going to be like, huh, that's weird. Round that right there. Round that R squared and interpret it. We're trying to understand test grade. We want to know someone's test grade. Like, let's understand why people have certain test grades. And we've already learned from a previous example that, here's the previous example on the side. We already learned that 91% of your test grade, see Emma? 91% of your test grade is explained by how long you've studied. 91% of the variation in your test grade is explained by how long you studied. Oh, a long time ago. We started using it like the day it happened, or like soon after. 20% of the variation in test grades is explained by the variation in cheeseburgers you eat. But here's the thing. Because of the small sample size, you're welcome, Abigail. Head on out. We will finish this up and we'll have more questions, so check it out. Tell me about the X's in these models. So look at the very bottom. Here's the cheeseburger X. And then over there on the other side, across on the same row now, is the hours studied X. Right over here. That's the hours studied X, the bottom one, the p-value for it. And here's the cheeseburgers X right there. So tell me about these p-values and what they mean to you. So the p-value of the slope tells us whether or not the model is statistically significant. So the p-value of the slope right here indicates that the first model has a statistically significant slope, that the relationship between hours studied over here, exactly the second one, is not significant. This is above 0.05, meaning that the relationship between cheeseburgers and your test grade is likely by random chance. Likely, we'd say not that it is, good work right there, Cameron. We'd say likely by random chance, like probably by random chance, because high probability, low probability over there, so not likely by random chance, likely by random chance. Notice how this has a lower R squared closer to 0. This has a higher R squared over here, and so this is the likely result by random chance, i.e. this p-value right there, and it is the p-value of the slope, to reiterate, and this over there on the far side is the unlikely by random chance, stronger relationship. So really good review right there. And one last thing, find correlation from this R squared. So do you see this R squared right here? Find me the correlation, but be very careful. Remember the steps for finding correlation. So find me the correlation. Find me the correlation. There's the R squared right there. Yeah, oh, look at the what? You're kind of right. Look at the, I know what you're saying. Yep. Correct. It'll be lined up with the X name. It'll be lined up with like cheeseburger is the name of the X variable, and it'll go across, and it'll be right here. For now, for us, it should be the second one on the estimates right there, the parameter estimates. That is correct, Ashley, right there. But just look across where it says cheeseburger, which is the name of the X variable, and then p-value with cheeseburger right there. And I can't trick people because you already know to look to see if it's negative or positive, and you have it right there. There's the correlation. So we could figure out the correlation via other output right there. So we could do it with the output over there and take it, square root it, look at the sign. The sign's negative, and good stuff right there. So good work. Can't trick you. Excellent job, everybody. And thank you so much. If you come back and watch this later, that's awesome too. I have a thing I got to do at 2, so I got to make sure to keep going with the questions. Here we go. Bright ant, lively alpaca, silly sphinx, inspired iguana, and yellow goat. Next question is, what is the best way to know the difference between p hat, y bar, p, and mu? Be very careful right here. We have p hat, y bar, p, and mu. So we're trying to know the difference between them. So think p hat and y bar, p and mu. Some of these are very wrong. Do p hat and y bar come from a population? Look at this. Right there. So I want to explain why it's that one. So this is a little tricky. I do know this is another tricky one, but the red I think is pretty also right. P hat is for proportions and y bar is for means. But that's the difference between p hat and y bar. Does that make sense? Don't worry if you got it wrong. That is, red is still a right answer. That's why I was like, oh no. But think about this. P hat is for proportions and y bar is for means. But that's the difference between p hat and y bar. But p hat and y bar are sample whatses, which means they have sample sizes. P hat and y bar are sample what word comes next. P hat and y bar are sample what word. I make the Kahoot a little bit hard, don't worry. Not distributions, they're sample statistics. Sample, good answers, Carrington. Sample statistics. And then P and mu are population whatses. So p hat and y bar come from samples because they're sample statistics. And then technically it doesn't have p and mu on here, but p and mu are population parameters, so they'd come from a population. So the key difference between p hat and y bar, and then to compare them to p and mu, is that p and mu come from populations, which would have a capital N for population size, and p hat and y bar come from sample statistics, which would have a lowercase n for sample size. Does that make sense? But this is correct. P hat is for proportions and y bar is for means. So a p hat would be like, I talked to 20 students and 14 of them have cats. What is p hat? I talked to 20 students and 14 of them have cats. What is p hat? P hat is the sample proportion. X is 14, N is 20. So what would be p hat? What's the sample proportion of people who have cats? What would it be? Yep, I think so, right? Because 14 over 20, 0.7. And then the sample mean, y bar would be like, I talked to 20 students and the average they spend a week on groceries is $120. Whereas I talked to, or I know the data on all UT students. I know how much they all spend on groceries. What on this screen would be that? So what on this screen would be that? Like I talked to all students, or I know the data from all students and how much they all spend on groceries. We're looking at spend on groceries for all students. I didn't take a sample anymore. What notation is that? If you knew for all students how much all students spend on groceries on average, what would that be here? Mu, because it's quantitative and it's for the population. Where if we said UT knows how many students or what percent of students are in-state or out-of-state, that would be P, because that's the true proportion of students for the population that are in-state, out-of-state. Good work right there. Let's go to the leaderboard. Silly Sphinx, Bright Ants, Lively Alpaca, Inspired Iguana, and Prairie Swan. Here we go, the next question. The central limit theorem is a what? Type it in the chat. The central limit theorem is a what? Not that you need to know this for the test. What is the central limit theorem? If someone misses this on the test, I will be really sad because I'm using this voice and I put it in the Kahoot. Does anyone know in chat what this is? I said this during class last time because I wanted to make sure you know it. So it was midway through our class. It's fundamental. That's one of our teaching to the test moments right there. It's a fundamental part of statistics, which means we need it. We use it so much. So states the over, the long run, repeated trials, we see the true probability. What is that? Seeing the true probability over the long run with repeated trials, that's not the central limit theorem. Don't worry if you got it wrong. But the true probability of an event over the long run frequency of trials, observing it, or being able to estimate, is the law of large numbers. States less likely events are more likely to occur in the future is the what? What is the thing that states things that haven't occurred are more likely to occur? What is the thing that states things that haven't occurred are more likely to occur? What would be that? If we say, oh, well, this hasn't occurred in a while, so it's going to be more likely, because I haven't flipped heads in a while. That's law of averages, exactly, which is a fallacy. It's not proper thinking. So that's the law of averages. Yeah, this is the fallacy down here, the bottom one. That's a fallacy, which means don't think this way. It's improper thinking. I mean, you could be right. Maybe you flip heads and you're like, I told you, but you got lucky. And then up here is the law of large numbers, which states if you look at the frequency of heads in the long run, you'll see the true probability over repeated trials. Good work. Leaderboard time. Silly Sphinx, Bright Ant, Lively Alpaca, Inspired Iguana, and Diplomatic Macaw. Macaw? Got a koala with a Viking hat. The conditions for the sampling distribution of the sample proportion are, what are they? You should know them pretty quickly. So what are they? The conditions for the sampling distribution of the sample proportion. All you really have to worry about is, are we past regression? So no more QQ, straight enough, no outliers, plot doesn't thicken. And then from there, what is the third condition? We always do random. We randomly select the data. 10% means select less than 10% of the population. And then we pause. It should only be between two choices right here. When you do proportions, nice job. I gotta say wow to that. Awesome work. It is success failure. The other option would be large enough n, but that's the sampling distribution of the sample what? Have this in your notes. The other one is the sampling distribution. If you did large enough n, that is the sampling distribution of the sample what? The other one, large enough n, would be sampling distribution of the sample what? Because we have two things. Look at the formula sheet here. Sampling distribution of sample proportions is success failure. You know what to do, right? And sampling distribution of sample mean is the other one. Great job right there. And really good practice. Hopefully people are watching this in the future too. But thank you so much for being here. Owen Wilson, wow.
Wow.
Wow. Brian Ann, Silly Sphinx, Lively Alpaca, Inspired Iguana, Diplomatic Macau. And we've got some good chances of t-shirts here. 3 people are going to win t-shirts. Going on to the next question. The large enough n states what? Oh my gosh. You got the numbers on the screen and everything. Oh my gosh. Pretty tough one right here. So I'm going to state it a different way, see which one lines up with it. It states first we must look at the original shape of the data. Next, we must know the sample size related to the shape. If it's normal, we only need 1. If it's skewed, we need 25. If it's very skewed, we need 100. So in other words, the less normal it is, the larger the n needs to be. The less normal it is, the larger n needs to be. So let's look at the central limit theorem here again. Great job. We got a pretty good distribution of right and wrong. And I got to say, you're my all-stars right here. Hey now, you're an all-star. You're getting 10,000 points in the chat. We get it wrong here to get it right on the test. Oh, I put a capital N on there, did I? Oh, I did, didn't I? The sample. Oh, some people got tricked by the cap. Oh, who said that right there? That we're throwing you just 20,000 points for noticing that, because that caught some people off guard. But the sample size, great job. We're throwing out some crazy points here. The sample size. Don't worry, I don't think we've ever written a test question just like this. Sometimes my questions are pretty tricky because I like to point out those little differences in notation. Little bits. So what you have right here is a normal distribution. So if I went out and spoke to 25 students, what would the distribution of their mean look like? Like the average student is 5'8", and there's a spread of 2-3 inches. And then I talked to 25 students. Here's me talking to 25 students, and I would get one mean out of it. There's the one mean. I would maybe theoretically do it again, or hypothetically I could get a different one. And so there's another mean right there. How many questions are on the Kahoot? 25. We're almost done. We're rocking and rolling. But here's the thing. If the original data is normal, my sample size doesn't really matter. Because if it's normal, the distribution of the, thank you, Ava, right there. If it's normal, the distribution of the sample mean will also be what? If it's normal, the distribution of the sample mean will also be what? If it's normal, the distribution of the sample mean will also be what? Normal. But here's the thing. I think I might be able to do this. What changes about this distribution? It becomes more normal and tighter, right? So the mean will do what? The mean will stay exactly the what? Here's the original mean. Here's the new mean. The mean stays exactly the same. But the standard deviation gets smaller by a factor of the square root of the sample size by which you're sampling. So, and we made sure this happened in class. Oh, we made sure that we have here a sample size of 5, and the standard deviation is now 1. Go ahead and compute for me the new standard deviation of this distribution. Ooh, I can almost, yeah, I got that. I got lucky on it. Compute for me the new standard deviation if we take a sample size of 25 from this. So the original standard deviation was 7.5. The new standard deviation will be what? The new mean will be 10.37 because the distribution of the mean has the mean as its center. The sampling distribution of the sample mean. Sarah got it right there. I got lucky because it's such a nice, neat number. And here's the thing. Watch this. Boom, right there. Because 7.5 divided by square root of 25, so you got it. Now also, this looks pretty normal, right? Pretty normal. Because this distribution is probably what-ish. So 25 is large enough. This is the large enough n condition again. 25 is large enough when the original distribution is what-ish. Like, kind of what-ish. Like, yeah, sure, this-ish. You can just put this one word. 25 is what we need in terms of sample size to make the new distribution normal if the original data is skewed. Yep, sort of skewed, kind of skewed. But what if it's super or heavily skewed? So if it's very skewed, which I'm going to go up here and do this. Oh, wait, sure. Does that help me? What I'm hoping is it's not normal. Darn you, central limit theorem. The central limit theorem strikes again. You need some really heavily skewed data to need more than 100. The more skewed the water n needs to be. So that's what it is the more skewed, the less normal it is, the more skewed it is, the larger the sample size needs to be, not the population size. The more skewed it is, the larger the sample size needs to be, not the population size. The population size is the original data. We need a larger sample size. So very key right there. The capital N, lowercase n, catching some people, because it's the large enough sample size condition right there, not the large enough population size condition. Okay, bright ant, silly sphinx, lively alpaca, inspired iguana, and classy possum. Here we go with the next question. Let's do it. How do we check the 10% condition? Nice and easy one right here. Conditions to check. What do we check for the 10% condition? What do we check? I go out and sample 300 UT students, and 150 of them own a dog. Do I pass or fail the 10% condition? So I'm going to write this, start a poll. I went out and sampled 300 UT students and 150 own a dog. Okay. 300 UT students and 150 own a dog. And so can you explain it to me now? And so you've got right there, the size of the sample needs to be less than 10% of the population size. And great job. Everyone's gotten it right so far with the answer. Why do we have it right? And a lot of people make an error when they see this because they're like, well, that's 50%. That's not it's not what you're checking. Because a lot of times you'll look at so if you got it wrong, if you're like, oh, but that's 50%. So write a sentence telling me why we passed the condition with 300 UC students were sampled, 150 own a dog. We do pass the 10% condition. Exactly, because there's more than 3,000 students, 300 students is less than 10%. But when a student does this, they go 150 divided by 300 equals 0.50, and they say we fail. They're not checking the condition. They're just finding what right there. So they're doing this right here. What are they finding? They're doing this, and that equals what? So what are they actually finding? Because they're not checking the condition. Not P, though. That's the truth. It answers William right there. They're finding the probability, and they're finding the proportion for the sample. X over n is p hat. P hat, that's the sample proportion. P is the truth for the full population, which we'll probably never know. Does that make sense? So they're not finding the truth for the full population. They're just finding what they saw in their sample. Like, I saw 50% of students in my sample owning dogs, but P would be like, UT knows that 40% of students own dogs. So P would be the truth, where P hat is the sample. Just a small difference right there. And that's what the question was getting at, that P is for the true proportion of everything, and P hat is only for the sample. Okay. Leaderboard time. Bright ant, silly sphinx, lively alpaca, inspired iguana, and classy possum back on the leaderboard. How do we check the success failure condition? Will there be questions on the exam that do not pass? There could be some, Ava. Good question, Ava. How do we check the success failure condition? UT knows. Okay. So if you look at the chat right here, go Vols. Thank you, Mubot. Oh, because I typed UT. Okay, so you have right here, see if NP and NQ are greater than or equal to 10. So remember what I wrote previously, that we talked to 300 students and 150 own dogs and 40% is the truth. Show me the numbers on passing/failing. So show me the numbers here. Tell me and explain to me the mathematics. Do we pass and how so? People are saying the answer to the question, but so 40% of students own dogs is the truth. Somehow UT knows that. They know the true proportion. That's not from the sample. From the sample, 50% own dogs. So you want to find NP and NQ. So N was 300 because we talked to 300 students. 40% is the truth. Q is 60% because P and Q are complements. 1 minus P is Q. So you need to do N times P is greater than or equal to 10, see if that is good. And N times Q is greater than or equal to 10, see if that is good. Boom, right there, you got it. Sarah, amazing work. Sarah, we're throwing you another 10,000 points. Going crazy on these Kahoots with all these points. Hashtag show up to the Kahoots and you'll get tons of points. You might even just get maxed out for the semester. Remember that for exam 3. Tell your friends, show up. Be like, I haven't been there all semester. Well, show up to exam 3, Kahoot. It's gonna help. So with this right here, Bright Ant in the lead, Lively Alpaca, Silly Sphinx, Inspired Iguana, and Classy Possum. Thank you for all those W's for Sarah right there. Keep it up, Sarah. The success failure condition states which of the following. Is this just a repeat question? Oh, well. I mean, sure, I just write a repeat question on here. Why not? W's for Sarah right there. You're welcome, Jameson. Head on out, don't worry. Hashtag show up to class. This is a Friday, so if you're here, you're just here to have some fun. Should be the same thing. You don't want quantitativity, you don't want identifiers. Binary, not really. Not really past Brian. We're looking for, you need at least 10 successes, at least 10 failures. We don't really analyze identifier data. Quantitative would be large enough N condition. Those right there. Back to the leaderboard. Bright Ant, Lively Alpaca, Silly Sphinx, Inspired Iguana, and Classy Possum. On to the next question. Probability of making a shot is 30%. What's the probability of the complement? And this is a good question right here. You should be quick on this because we just did P and Q. So P and Q are complements. So we could say in a question, P is 0.3, and you should know what Q is like that. So P and Q are complements. So you should know how to get complements really quickly. If you're like, P is 0.3, Q is 0.7. What if P is 0.98? What would Q be? Oh, great job, Sarah, with those amazing notes. P plus Q equals 1. So you would just solve that equation right there and get the complement. If P is 0.98, Q is 0.02. Great job, Carrington. Also, let's throw Carrington some big points too. Thank you everyone for being here and practicing. Remember, P and Q are complements. Complement is 1 minus the other one to get the, or 1 minus it to get the complement. And so going on here to the next question. Bright Ant, Lively Alpaca, Silly Sphinx, Inspired Iguana, and Classy Possum. The law of averages is a fallacy. The truth is what? Law of averages states that things are more likely to occur in the past. So if you have events that have been occurring, they would what each other? Like if they're completely, like flipping a coin is completely what? Flipping a coin is what? Be completely independent of other trials. Great job, we're doing really well. So past events do not influence independent trials. Law of averages states that if you flip a coin, you're more likely to get heads if you haven't gotten in a while, but that's not the truth. You're just, independent trials will not influence each other. Go, Bright Ant, Silly Sphinx, Lively, Epic Dolphin. Good job, Lively Alpaca, Inspired Iguana. Next question. We know UT is 20% freshmen. We sample 200 students from 30 report being freshmen. What is N? Nice and easy question to start. It's just using your notation skills. And is this quantitative or cat? For a cat named Quant, is this quantitative or categorical? Is this quantitative or categorical? Is this quantitative or categorical? It's categorical because UT is 20% freshmen. Have your calculator out. We're about to do some calculator questions. This is the easy one because lowercase n stands for sample size, and it should be pretty easy to get the sample size here, and the sample size is n. Now, don't worry if you got it wrong, but make sure you write down, and let's review what the notation is. N is sample size. 30 is the amount who report being freshmen. So 30 is what in notation? N is how much you sample. So that's what N is. N equals sample size. Write that down. And then 30 is the amount of successes in a sample, not p hat. Good. And p hat can only be between 0 and 1. Sophie, 10,000 points. Keep those answers coming. It's not p. P is the true proportion. Not p hat. Don't worry if you get it wrong. This is why I ask these questions and I pause on these things. We sample 200 students. N equals 200. So what is 30? 30 is not p, though. It is X. Great job, Sophie. Sophie, another 10,000 points about recovery. Just keep answering questions. Look in your notes. Uppercase N is population size, which would be the size of the UT population. So lowercase n, we sample 200 students. That's our sample size. Uppercase N, population of UT students, 30,000, which is not listed here. The amount of successes, and Hannah's following through with a little p hat right there. Great job. Why is it X? X is the amount of successes. It doesn't mean variable X. It's a notation that just means X is the amount of successes in a sample. So there were 30 out of 200 successes, and X over N is p hat. So Hannah's found p hat right there with X over N. It doesn't mean variable X. It just means X is the number of successes. We, for some reason, just like using X there also. And then did people figure out what 20 is? We know UT is 20% freshmen. We know this. It's the truth for all the university. I don't know why we have fewer freshmen, it seems. We should have like 25, 30%. That is P. That is the true proportion. And from P, you can find Q, and from P hat, from 30 over 200, you can find Q hat. Is it making more sense right here? Practice this notation. Know which one is which. P equals 0.2, Q equals 0.8. Great job, Hannah, right there. And just know what the notation is. Have it written down so you can be like P equals the true proportion. That way, when you get to your formula sheet, you're like, that's what I need right there. Good work. Next question. Have your calculator out. Bright ant, silly sphinx, lively alpaca, inspired iguana, epic dolphin. So when we do the standard deviation, we use P. That is correct for this chapter. More to come later. We'll see it later. Yes, right now, yes. What is P? So if you're listening in, you should be able to find P here pretty quickly, which will also be mu P hat. P is also mu P hat because the proportion, or the true proportion, is what we expect to see in a sample. So P would be equal to mu P hat. The mean for the distribution of the sample proportion is equal to the true proportion. So what is the true proportion? Well, it's something you know. So the true proportion is what? The true proportion is, and it's got to be a number between 0 and 1, so it has to be P right there. Now be careful. This value is not the truth. It comes from the what? P is the truth. That value, 30 over 200, comes from the what? This value right here, 30 over 200, comes from the what? It's not the truth. It is observed. I'll take that right there. Good answers, Cameron. Cameron and Hannah, we're dropping you both this. That's X over N, which is from the sample. It's P hat. So that is P hat because it came from the sample. That's the sample proportion. Like we observed in a sample, you can say observed, and then you can even say expected. The population is what you expect, and that's where you can do the z-scores, which is maybe where you're going with this. So that terminology does apply. Specifically, P is the true proportion, P hat is the sample proportion. You could say I expect to see the truth, and then you can call it the expected value. So a lot of good terminology. Continuing on, Ethan and Lily, great work too. Bright ant, silly sphinx, lively alpaca, epic dolphin, yellow goat. Here we go. UT is 20% juniors. From 80 students, 30 are juniors. Find the mean of the sampling distribution. Now, this is where people get stuck. We need, quote, 191 P times Q over N square root. Try to find it quickly. P times Q over N square root. P times Q over N square root. P times Q over N square root. P is 0.2, Q is 0.8, because they're up there. The truth is 0.2, the complement is 0.8 over 80 square root of the whole thing. P times Q over N, quantity square root. It's the whole thing square root. Only a few of these answers, or only one of them really makes sense. Did anyone get this right because they looked at it logically? Oh, wait. Oh, the mean. Did I say standard deviation? Did I say standard deviation? Oh, no. Oh, no. I'm so sorry. Was someone in first and they dropped from first? Was someone in first and they dropped from first? Was someone in first and they dropped from first? Only 2 people got this right. I don't know who leader. Valeria, you were in first. Valeria, you won a t-shirt. You won one. You won. You just, boom, right there, you're a winner. You sit back right now and be like, I won. Because Brian read it wrong. He said standard deviation. He was having to solve the standard deviation. So Valeria right there, winner, first place. We're going to keep going, though. So good job right there. I felt so bad about that. Also, if you were in a higher, or like, was there a second place that immediately dropped off the leaderboard? Because only 2 people would have gone up. Got this right on accident. Oh, was it me? Okay. Oh, was it you? Okay, so this asks what the mean of the sampling distribution is. So the mean of the sampling distribution of the sample proportion is equal to the what? The mean of the sampling distribution of the sample proportion is equal to what? The mean of the sampling distribution of the sample proportion is equal to what? The mean of the sampling distribution of the sample proportion is equal to what? That's the mean for the sampling distribution of the sample proportion is equal to P. So all we have to do in this problem is find what? Because we're trying to find this. So all we need to do is find that. The truth, exactly. So what's the true proportion? If you read the problem, UT is 20% juniors. So the true proportion is 20%. So if you go out and take a sample, you expect to see 20%. That's what expected sample proportion means. It means if 20% juniors are out there walking around UT, that's what the population is, 20% of them are juniors. Well, if I go out there and talk to them, I'd expect to see 20% juniors in my sample of 80 students. And that's the expected sample proportion. And then standard deviation coming up here next, probably get some quick answers. Leaderboard, Bright Ant, Silly Sphinx, Lively Alpaca, Epic Dolphin, Yellow Goat. Here we go with probably an easier question. So what is P hat? I think you'll get this one, not the standard deviation. What is P hat? What is the standard deviation? Oh my God, what is P hat? What is wrong with me? What is P hat? I'm all ready to find the standard deviation, but this is P hat. Read the questions before Brian reads them. He will try to trick you, maybe on purpose or not. P hat is x over n. So x over n is the amount of successes over the number of trials. So you take x, which is 30, over n over 200. And it's going to be that right there. There we go. X over n equals this right here. We got it. Good to go. Good to go. Maybe last question of the day, but first the leaderboard. Silly Sphinx, Bright Ant, Lively Alpaca, Epic Dolphin, Yellow Goat. Here we go. 25 of 25. What is the standard deviation? Now this is the one I've been waiting for and I already gave away the answer to. Now when you come across a problem like this, you first want to ask yourself, is it categorical or quantitative? Categorical or quantitative? Since we're asking if people are juniors, it's going to be categorical. So since you've recognized that this is a sampling distribution question asking for the standard deviation, and we're asking juniors or not juniors, you go to your formula sheet and you say, I'm looking for the standard deviation. Now it's only going to be one of these 2 formulas. But notice, once you identify its proportions, you just need to now find P times Q over n square root. So you go back to your problem and you say, okay, well, P is the true proportion, which is 20%. Q is the complement of the true proportion, which is 80%. Divided by 80, and then square root of the quantity. Don't do a P times Q over n square root. Do P times Q over n square root of the whole thing. You should get, leave that right there. There we go. Does it make more sense? I hope so. The things we didn't do today is we didn't do sampling chapter that much. So we'll probably be reviewing that next class. Check out the videos, the review 2 videos. But really great work, and please swing by my office if you won. Great job to everyone here and watching this in the future. We only have 11 students right now. I knew doing this early might be a little bit, maybe I should never do them this early, but I want people to have this as a resource. Let's go check out that leaderboard. And we don't get the announcements. Silly Sphinx, Bright Ant, and Lively Alpaca in first, second, and third. Amazing work right there. Really great job with those cool shades. They give you like cool shades at the end. Or did you both pick those shades? Thank you, Ava, so much for being here. Thank you, Lily. I'm going to go grab a quick energy drink before my next thing I got to do. Doing some stuff. Thank you, Mary, right there. Keep up the good work. I picked those shades. Well, those might be the winning shades. Those are some, if I had some shades like that, that'd be pretty cool. You're welcome, Carrington. Where's my office? The 2nd floor of Stokely Management Center, right next to Haslam. Swing by and be like, Brian, I'm here for sure. I'll be like, you got it. Still got small, medium, larges, and I think some XLs, whatever size. We probably still have yours. Maybe it'll be like a night shirt for you, or maybe I don't know. We should still have enough sizes till we get down to the last few shirts, and it'll be like, well, do you know someone who wears a large, or you know someone who wears a small? But right now, we've got shirts. Until then, and great job right there, Ava and everyone else who won, it looks like. Until then, bye for now, everybody. Bye. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.